Good, yeah, thank you. Is it? So it should look then something like this. Is it working on every computer? Okay. Yeah, so the idea of this session is to actually start to build your own sequences and play around with, and just use different building blocks which I prepared to get your maybe first experience in writing MR sequences. All of them could run on a clinical scanner as well, but that's not the topic of today's session. So we will very quickly. So those images you already saw, and essentially most of those sequences could be created by just a few building blocks, which I created here. So that's just the complete set of building blocks, which would show up at the start. I also prepared sort of an simplification, which hopefully makes it a little bit easier for you to get started, because it hides some of the functionality of the tool. But let's get started with the tool itself. So that's how it looks like. The principal content. Oops. The principal content is that we have on the left side just a list of all the different building blocks, and there is also above what's called a lecture. You can select different lectures, and then it will just start to hide most of the functionality and just present a very simple set. And that's just for different topics, and we will go through some of those lectures, but we will still make some modifications if needed, playing around. But for you, it should be relatively easy just to switch between those different lectures. You can always, even within a lecture, activate other of the building blocks by just clicking at the different tags up here. So, for example, if you want to get all RF pulses and all gradients, you could just activate them, and you would just get additional stuff in. So you do have the full flexibility. It's just sort of a pre-filtering for the lecturing, and it's also presetting the other modules which are part of it. So the next component, so you can grab any of those building blocks, like a 90-degree pulse, and move it to the central region here. And the central part is essentially just the MR sequence, as what we call the sequence diagram. It's just showing in this case, I'm showing. So if you select the lecture 1, it will be pre-configured that it shows if you remember, we had 5 different components. We have the X gradient, Y gradient, Z gradient. We have RF transmit, and we have receive part of RF. And RF is either transmit or in receive. That's why in most of the times everything is just put into one curve or one waveform. So this diagram up here would just show everything which is related to the radio frequency pulses or the data acquisition will end up here, and then the different gradients would have different diagrams here. Right now we are not using any gradient. So not for you to repeat, but just to show you how it would look like for a complete sequence. It's really a little bit strange with the here. So we can look at a complete sequence, and a complete sequence then would look like this, for example. Yeah, so we would have an excitation pulse. Then we have a readout, which is just marked by those stars here. And then we are switching gradients. This is along X direction, that's along the Y direction. So that's how a sequence would look like. Yeah, and we will come back to this later, but first start a little bit more simple, just to show you this view. That's the standard view we would be using for looking at a sequence and looking at the different components of a sequence. For us, we will start with RF pulses only, and then continue adding gradients and other stuff. So we would rather go to a more condensed display, which allows us to also show information about what's happening to the magnetization. And for this, there's on the right side, we have something which is called the Bloch simulation, and I will come back. Klaus already mentioned about Bloch and Bloch equations. I will come back later to this. That's actually the mathematical way to describe how our magnetization performs after during applying RF pulses, gradients, whatever. So with this, we can calculate what's happening. And that's what this system actually does. So it calculates the behavior of your magnetization for whatever you have in your sequence diagram, yeah, whatever it's showing there. And the display is there are different ways how to look at this magnetization. So you could either look at the plots what we had before, and maybe I start to show you. So I delete everything, go to lecture 1. So that's what you can follow. So moving a 90-degree pulse over. So right now we would have the gradients. I said gradients we don't need. So we would switch to another visualization mode by just going to this visualization. And I would recommend for you to use this simulate extended. And all the other lectures will pre-configure this extended simulation mode. Because that one moves everything which belongs to the sequence into this part here. So there are the RF pulses, there are the gradient pulses, everything is just put up in there, but it still gets not too crowded, so you will still have a nice overview. And then they have two actually diagrams being added. One is for the longitudinal magnetization, and one is for the transverse magnetization. And if you look at the far right side, we are already seeing some arrows here. And those arrows just mark the magnetization at this exact location. So relatively simply, and simple, and we have 11 by 11 magnetization spins. And for each of those magnetizations, we have one line in this additional plot here, which is shown by different colors. And for the transverse magnetization, there are two parameters which can change. One is the intensity, the length of my magnetization, and the other one is the direction. So it could show in all different directions. Yeah. And the direction is encoded by color. and the intensity just by intensity. So you will see that it becomes weaker and weaker over time. And for the longitudinal magnetization, we only have the amplitude. There is no phase. +1 is bright red, -1 is bright blue, and then 0 is white, and then it just has everything in between. So we have for each of those magnetizations, we have one line, and right now they are just behaving exactly the same, but you will see later on that there are changes and that it is changing. You can, with a right click into your sequence, you can look at how the magnetization looks at this specific time point. Yeah, so regardless where you click, you will just see that your 3D viewer will adapt accordingly and will change. And transverse magnetization is also creating some shadows down here to give you some impression about what's the part which is creating signal. And you can zoom in here and look at the different points. And you have also quite a few ways to configure your magnetization, whatever you like. You can either use some presets which are provided here. For example, you could color or make the color of your magnetization dependent on the phase of your magnetization. And by using that one, oh no, I switched to another setting, which has a stronger magnetization, sorry. So then the color of the spins will have different, will have exactly the same color as in your sequence diagram here. And by clicking on settings, you can just modify some more settings. I think most of the time you will just adapt the size of your magnetization so that it's just more visible for some extent. Yeah, and then you can just also automatically play by clicking on display. You can just go through what happens to your magnetization, and there you see magnetization is just flipping around to transverse magnetization. So it's relatively simple. Yeah, what else to say here? I think that's it for now. So now we can start to look at some T2 relaxation, for example. What does it happen? Oh, what does it mean? We have our excitation pulse, and now we want to look at T2 relaxation. Just making sure, yeah, that's fine. That means we have to actually wait for a certain amount of time before we are looking at the image. Yeah, or not the image, at the magnetization right now. So we can zoom out. You can either use a mouse with zooming, or you can use the touchpad two-finger sign to zoom out. Sometimes if you have a lot of spins to simulate, it's more easier to just undo this auto update. Auto update means it is doing the Bloch simulation anytime you are changing anything in your display, because it's always calculating the magnetization relevant for what you are seeing in your display. If you do experience troubles, I think with 11 by 11, the systems should be fast enough to just zoom out more or less in real time, and it will automatically simulate an update. If you are simulating more magnetization pieces later on, so you can go up to, I think, 100,000 or so if you want to simulate. it might be better to just unclick this auto update so that it's not automatically updating, but you can just do the changes to your display or add additional pulses, however you like. And then this update button will turn yellow, telling you that you have to update to get the current results. And then you just click on it, and then it will do the calculation. Yeah, so that might be a little bit tricky otherwise. And here we already see that we are getting the T2 relaxation over time. Yeah, so the signal becomes weaker. And if we play our magnetization or how the magnetization actually behaves, you will see that parts of it, so the transverse magnetization decays over time, and at the same time longitudinal magnetization is starting to build up. Yeah? But the orientation of our magnetization doesn't change. Yeah? So it's always the same direction. And of course, you could say, okay, but why is the phase always pointing this, to the same direction? Didn't we say that we are that our magnetization is precessing all the time? And of course, we could do it, but then it would start to spin. If we would be realistic, it would spin 128 million times per second. It's a little bit fast, so there is an easier way how we actually look at such images. And that's actually by, we have to switch back. Which one is it? This one. I have to look. So we can, so we should be, yeah, that's not working. I don't know why but what we should see is that our magnetization is precessing, as I said before. And because this precession motion is so quickly, it's easier to go into this reference center, this isocenter. If you remember, I said we could define this to be our reference. And if we do this, it would mean that, I need my magnetization back. So it means that our magnetization, which is precessing, we are now going into a different coordinate system. And the coordinate system we are now using is the so-called rotating frame, or the rotating coordinate system. What does it mean? It just means that we are following those, or this magnetization, which is sitting at isocenter. And we know it's precessing 128 million times per second. But we are just going exactly the same. So we are rotating exactly 128 million times as well. So we are following this magnetization. So for you, the magnetization is moving and it's precessing. For me, it's just not moving at all. It's always in the same position. It's always there. And that makes it quite simple. So in the rotating coordinate system, my magnetization is just always in the same position. And can switch. So that's what we are looking here. So we are actually here simulating in this rotating. I don't do it again because then I get dizzy. But so we are always looking within this rotating frame. So here, because we do not have any additional magnetic fields applied, they all see the magnetic field at isocenter, so they are not moving. Yeah, so we are looking in this rotating, in this rotating frame or coordinate system, and that's what it actually is. And since it's not precessing, in the rotating frame, there's no static field. So mathematically, we can simplify all our calculations, just assuming there's no external magnetic field. Because as I said, the precession velocity, the physical law, directly depends on our magnetic field linearly. And if it's not moving, then there can't be a magnetic field. Yeah, so by doing this, this transformation from the laboratory coordinate system, where everything is precessing and a static magnetic field exists, we are now going into a rotating coordinate system, and this transformation actually transforms. First, it leads to not moving magnetization anymore in that case, and it also allows me to transform the static magnetic field back to zero. Yeah, so it's a mathematical trick, but it's quite efficient and it simplifies calculations quite a bit. Mathematically, you could think about before you had described something like this precession motion flipping down. So you had to describe this spiral or cone motion. Now it's just flip. That's it. So mathematically, that's much easier. And that's why we are using this, this rotating frame coordinate system. Yeah, so that's what it means. Law of physics remain the same since our magnetization is not moving. The B0 field has to vanish. What does happen to our applied RF field? We typically call the static field B0, and the RF field which we are applying we call B1. And remember our RF pulse, because our magnetization was precessing before, our pulse which we transmitted had to rotate and actually circulate as well. But now it's pretty simple. Even though we are applying a high frequency RF pulse, but in the rotating field, it feels just like a constant magnetic field. Yeah, while I switch on the magnetization, this transmitted RF pulse, although in the laboratory field it's oscillating 128 million times, in the rotating frame it's static. It's just switching on an additional magnetic field. And what does happen to magnetization if I apply it from here an additional magnetic field? It's like what we had before. Our magnetization starts to precess. It precesses much more slowly because this magnetic field which I'm applying with my RF pulse is much smaller. But it allows me, by switching this additional magnetic field on, to let my magnetization precess. And just depending on how long I leave it on, I can decide whether I want to have a 90-degree flip angle or a 180-degree flip angle. If I leave it twice as long on, I will get a 180. If I leave it still on, it will just have a 360-degree pulse, for example. Yeah. So by the duration of my magnetic field, I can actually distinguish or describe which flip angle of my magnetization I'm getting. Having a longer RF pulse will create a larger flip angle, 180 instead of 90 degree. I could also make a stronger magnetic field. So if I would use twice the amplitude of my RF pulse, the precession will be higher, and it will be twice as high. So if I double the amplitude of a 90-degree flip angle or 90-degree RF pulse, it will then result in 180 degree, twice, 2 times 90 degrees. Yeah. So I have two ways to actually decide or determine how I want to rotate my magnetization, and depending on from which direction I apply the magnetization will either be flipped in this direction, or if I apply it from this direction, it will be flipped to this direction. And we can try this on with the tool. So if you have zoomed out, you can click on Reset View, and then it will just zoom in a bit so that that it's a little bit easier.
Switch the screens.
Oh, that's a good point. Thank you. Yeah, that's something I have to memorize. You can click this Reset View, and then it will just zoom in if you have zoomed out too much. And actually, it is possible to, as I said, I just updated. So right now, the magnetization is flipped to a phase which is shown in green here. Yeah, and in green, so looking at the viewer here is to the leftish side, whatever. Yeah, flipping it over here. If we want to, that's actually flipping my magnetization from this direction. Now we want to flip it from another direction. So we just want to apply a different RF pulse or coming from a different direction. And there you can just do a double click on this 90-degree element. And there you have 3 parameters you can change. So first is the amplitude of your pulse, which would yield a different flip angle. Yeah, so if you increase it or reduce it, you will just get a different flip angle. And I already calculated it so that it's showing the, your flip angle. So it is giving you the flip angle in degrees. You can modify it. But if we want to apply it from a different direction, we have to change the phase of this pulse. So right now, and I don't want to go into detail at this point, we are using an RF pulse which is not using a constant amplitude. That's a typical RF pulse we would be using in for imaging purposes. That's why I'm using it here. It's called a sync pulse or a modified sync pulse. It's just, we will come back later to this. The Fourier transform, just a second, Fourier transform of the sync is in rectangular shape. And maybe that already is sufficient for a hint why we are using those sync pulses. Do you have a question? Or?
We don't see the amplitude parameter.
You need to double click in the...
You double click and then it's only showing the frequency and the phase. Yeah, then you might not. Did you use those this basic relaxation lecture, or because I do have some predefined pulses where you can't modify the amplitude.
I think we also have the same. You are choosing to work on yourself. Just pay attention to the issue. Say I'm using so just from lecture. Drop down into basic relaxation, basic relaxation. Then choose the scroll down into articles, then choose 90. Yes. We have the same problem
Yeah, so the tool allows to also describe just some predefined where you can't modify it. If it doesn't work, what always works? Thank you. So, yeah, and if you want to apply it from a different direction, you would just change the phase. And the phase is also given in degrees, so you can here modify it by 45 degrees. If you want to, instead of from this direction, having it from this direction, we would just change the phase by 90 degrees. And if you have a look down here right now, the the RF pulse is played out along the x-axis. And if you then use 90 degree here, click on OK, you will see that it now says y-axis here. If you would have 45 degrees, it would be the XY direction. Everything in, and now you can see that the color has changed up here. So you're now we do have a different phase of our magnetization, and if we just click on it, we see, okay, now it's, instead of shifting it to the upper left side, it's now to the lower left side. Yeah, and of course you can change it for any arbitrary direction, which allows you to move your magnetization in any direction you want it to have. And that just adds the whole flexibility. So if you want to, you can also have inversion recovery part. I think that's something you can play around with this afternoon. There we will have a 2-hour slot where you can test different stuffs with a tool and also solve some exercises if you are interested in it. So yeah, I think that's the most simplest part, by just looking at your relaxation part. But of course, it would be a little bit nicer to not only look at magnetization, but also look at the image contrast, what we had before. So there, I think we, yeah, for this, we have to introduce our gradients. And we can go to the next lecture if you want to. And there we now get a little bit more pulses. And there it might, in fact, not be possible to change the signs, so the amplitude. That's why I just provided several flip angles here. But you can always go back to pulses where you can modify everything by clicking on templates. So activating templates. Those are the base elements which I use. So if you very eagerly want to control everything, as I typically like to do, you can go to those templates and then you can modify a lot of different stuff. Might be too much. That's why I just went back to those predefined pulses to make it a little bit easier for you, just to let you know. And there we now have gradients. We can do a lot of different stuff. And we can look at what gradients actually do to our magnetization. We first create our transverse magnetization again by moving in a 90-degree pulse. And then you can select any of those preparation pulses, gradient pulses down here. And those are just gradient along x direction, gradient along y direction, or the gradient along the z direction. Right now, our simulation, we just set it up that we are only looking at magnetization within the x and y plane. So preferably you would be using either an x gradient or an y gradient, and move it in. Make sure that it is happening after the excitation pulse. Since it is changing the precession frequency, gradients won't have effect on longitudinal magnetization. They only affect the transverse magnetization. And what they do is actually that they change the phase of the magnetization, and they change it differently in different positions, yeah, depending on how strong the magnetic field in that particular location is. So if you now click, so we first have our inverted magnetization, and then we make a right click to in the region where the gradient is. you see that your spins are already starting to have different precession. To make it a little bit more clear, you can click on the settings here and choose for the color mode phase XY, and then the color will just give you the phase, and then it might be a little bit more clearer what's actually going on. And what is happening? Our magnetization, let's look from the top. And I'm switching off the shadows to only get the pure magnetization. So we have the center of our, the isocenter is located here exactly in the center of our magnetization. So there, if you remember, the gradient was going from minus a value to plus a value, and in isocenter it had 0, so there's no additional field. So there the magnetization will just stay exactly the same. But in the regions which are further apart, depending on which direction, it will either be higher or it will be smaller. And the farther away from isocenter, the stronger the magnetic field will be. So the precession velocity will be higher the farther you are away. And if you just zoom into this region of the gradient, that's a little bit too much. You can just, if you have your auto update on, if not, just click on the update again. There you can directly look at what's happening to your magnetization if you switch on your gradient. So you see that the magnetization, those which are far away, you see it first because they have the strongest effect, and they will just start to precess more quickly. And you see this one up here is precessing in this direction, and down here it's precessing the other direction. Yeah, because there the field is smaller, in the other direction it's higher. And after you have switched off your gradient and not playing out the gradient anymore, the phase will just be kept. And it will just stick to this phase, what it has there. Yeah. So what we now did was to imprint a pattern on the face of our magnetization. And if we look at the sum of our signal, this goes down. So that's this dark curve here, this black curve, that's giving the sum of all the magnetizations. And since they are now showing in all other directions, they sum up to almost 0. Yeah. If they are not as much dephased, like in this case, they still reduce the magnetization we can measure, or the signal we can measure. Yeah, the sum of all of those. But it's still positive, so there is still something we can measure. And we can actually, if you use exactly the same pulse in again, you could just double the effect. So that would mean by clicking here, the magnetization will just get even further dephased. But what you could also do, if you double click on that pulse and then just use a negative sign for that gradient, so typing in either minus, or you could also give in -1 times in this expression field up here, it would just play out exactly the same gradient as before, but with a negative sign. And that will just, because now those which have been in the higher field regime will now experience lower field, and it's exactly balanced so that after playing this out, everything is aligned again and is showing in the same direction. And that's what we would call a gradient echo. Yeah, so we are first dephasing our spins, and then we are starting to rephase them. And the time where they were just the area between those two pulses, gradient pulses, is 0, the sum of the areas, then everything will be realigned again. Yeah. So that's the simplest part you can do with gradients. Yeah, so you can create spatial patterns. RF pulses change the orientation of your whole magnetization. Gradients influence the phase of your magnetization at different locations differently. Yeah, so they imprint a spatial pattern based on that. And we can actually make use of this to do imaging or to make imaging. So at this point, we won't go too much into details. You can just move this image readout over. So we now have excited our magnetization. Yeah.
Just a question for the gradients. If we make the ramp like long enough, then you will be having the dephasing become rephasing.
Yes. So that's a sort of a simulation artifact because we are only simulating 11 spins. And so even though one is precessing much more quickly than the others, there's always a point in time where they all will show in the same direction. But physically, they have accumulated a lot more additional phase, as we call it, yeah. So that you would be getting this this artificial echo, and it's a so-called aliasing effect of the simulation. You can very easily test it by increasing the number of magnetization or spins you're simulating, and you can do it. I will show you in a second how you can do it. It would take longer, but then it will just also have more spins to simulate, so it's less likely that they show in the same direction. There will always be some time, so the simulation is really limited in that regard. You will always get those aliasing artifacts, and you will always be able to get rid of it, adding more spins. But at some point, it's just inefficient for our hands-on simulation. That's why I chose this, and that's why we see this this maybe strange-looking artifact.
For the case you applied for the gradient echo, like the rephasing will not be like perfect, right? Normally, when we saw the magnetization vectors, it seems like it is like perfectly rephased. But normally, in practice, it will be not like that, right? Because we will have some kind of imperfections.
We will be coming to this in a second, yeah. Exactly. Thank you. I just wanted to introduce this imaging part first without spending too much time on talking about K-space because time is running. I think when do we have to leave?
Well, we should be ready at 1:45 to start.
But we have lunch at 1, right? Okay, good. I don't want to dig into the imaging part at this point, but rather assume we do have a readout. We are able to read out images, and they are actually switching gradients as well. And if you want to zoom in, the readout we are using here, that's a so-called EPI readout, which is just reading K-space in a zigzag pattern. And you might be able to appreciate how this zigzag pattern actually looks like by looking at the gradient pulses here. So it is, if you know that switching gradients makes your magnetization actually move in K-space. So if you apply a gradient, then you are acquiring different parts of this K-space. If you remember, or if you look at this pattern, what a gradient is actually doing to your magnetization, it's creating this stripe pattern. So we are probing our system with this particular stripe pattern, and the longer we leave it on, the more the finer this stripe pattern will look like. I can show you, maybe, sorry for jumping around, but maybe it makes sense to show this to you right now. With a simulation, so here for the Bloch simulation, we can also modify some parameters, and we will go in this every now and then. We can just use 200 and 200 by 200 spins along one direction. So you already see it takes quite a while to calculate, and that's why it's not really feasible for playing around with this in real time. So typically I would just switch off this auto update if I'm using so many spins. And since it doesn't make sense to have 40,000 lines in here, I also switched off this color display for the simulation part. So we are only getting the T2, the longitudinal signal, and the transverse signal, longitudinal and transverse signal. And then we can just look at what's happening when we are applying this gradient. So we are just updating it again for this region. And then we can just play the animation. And you will see that applying this gradient will just create a pattern which is changing. This gradient is not very strong, so we can go to a somewhat stronger gradient. Let's say we make this 40, and we could even make it longer. So that's the, right now we only have a triangle. We can also make it a trapezoidal shape by adding a time here, like 2000 or whatever. And then you see the shape changed and the amplitude changed. We can do the simulation again. And then you will see that you are getting, if we now play, you're seeing that we are now getting, oh, now it's a little bit too fast. So depending on how long we leave the gradient on, you see that we are getting an additional this stripe pattern, and the longer we leave this gradient on, this stripe pattern will get finer and finer and finer again. Yeah, and that's just because our spins are precessing at different velocities. And so this go to somewhat smaller. That's too small. And then it might be easier to. So if we only look at, we have to look at this axis. So you can directly look at. No, it's not too nice. So we take this top view. So there, the longer we leave here, the gradient on, we will get this stripe pattern. And this stripe pattern is associated to K-space. So switching a gradient and leaving it on means I'm moving in K-space to different positions. And for imaging, we need to cover the whole K-space. So what EPI actually is doing is that it just acquires the whole K-space by zigzagging through K-space, switching gradients on and off. And this gradient switching, just going to a somewhat more feasible way. The gradient switching will just recover K-space. And if you look at the signal, we have less signal in the outer reaches of K-space. So if you remember how K-space looked like, I think I do have a slide here as well. Yeah, I'm talking too much about those which I already told you about. No, that's still about the relaxation part. Where's K-space? Yeah. So if you remember, we do have the highest signal in the center, and then it falls apart at higher for the finer stripe patterns, so for the higher frequencies, and that's exactly what we are seeing in the simulation part here as well. So it is reading out the signal and it is hitting K-space in here in the center. If you carefully look at the phase patterns of all our magnetization, you already see that we are getting the finer frequencies acquired here in this central part. Maybe it's more obvious if we go to a smaller number of spins to simulate. So whatever there, it might be a little bit easier to see. So here now you can nicely see that at this region it's just less rapidly changing. Yeah, so those are the lower frequencies you are acquiring. So that's the part of the magnetization level, looking at the individual magnetization. And we can also, if we are doing imaging, you can switch off or go to another form of display. So you can switch off the Bloch simulation and the 3D viewer here, and then switch on the simulation part if you want to. And this is actually doing a simulation based on some phantom data. This phantom data is coming from BrainWeb, simulating or resampling one slice of the head. So you can either have the auto update on or off. Maybe it's good to not have it on, and then you just click here and it's simulating an MR image. And then you are getting an MR image of the sequence you have right now. So now what we are getting is we are exciting our magnetization, and we are moving we are moving through K-space to acquire this data. That's the part here on the left side, and then doing a Fourier transform of that one. And then you will be getting your simulated brain. And then, not your brain, but the simulated brain, the phantom brain. What you now can do is, in the upper row here of your sequence diagram, there are those different boxes. And red is typically an RF pulse, blue are gradients, and green are readouts. You can grab this by clicking with your left mouse button and move it around. So you can just say, okay, you excite your magnetization, and then you just leave it for a while, and then you're reading out your signal. And then again, your image will just show here yellow. So you have to click to get your updated image, and then you are getting a differently looking image. You can activate the auto update, but I realized if you have your auto update on and you are deleting your sequence and you do not have any readout block in there, or no, you could have a readout block, but if you do not have any RF pulse in, the simulator will crash. And then you have to restart it. So be careful. So and changing lectures will also include this deleting everything. I have to bug fix this. So that's if you're playing around with just existing blocks or want to add some blocks, then it's fine to have this auto update on. But as soon as you want to go to another or delete anything, please just either use this or unclick this auto update, or you can close the whole simulation part by clicking here on the simulation. And then it will automatically deactivate the auto update. But if you have the auto update on, it might be easier to see how the image contrast changes. So if you do not have much time in between, you get a very nice image. But if you have a long period, let's say whatever, 200 milliseconds between excitation and the image readout, you see that there's something going on. Actually, there are two things going on. One, of course, is you remember we now increase the time between putting our magnetization into the transverse plane and reading the image out, which means we are getting T2 weighting. The phantom itself has an additional property, and it is a little bit more realistic than what we were looking at before with our magnetization, looking at the individual vectors, because it is also simulating changes in local magnetic field. So we call it B0 inhomogeneities. So that one is also simulating more or less realistic changes in magnetic field you will experience in brain images, and especially in the frontal part where you have this interface between air of the sinuses and tissue of the brain. Up here there will be, because they have different magnetic properties, and those have, because of the strong external magnetic field, they have to assimilate somehow, and that's done by forming a local field gradient. And this local field gradient leads to an artificial gradient. So I get spatially differing magnetic fields. And that's actually in there. And we can have a look at this with our Bloch simulation. So you can now either leave the image on if your screen allows and switch Bloch and the 3D viewer on. But you see there is not a lot of space. So that's why for now I would just switch off our the simulation part here. But what we will do now is go to Bloch simulation. And then you can click on the use current phantom up here. So then it's borrowing the information from this imaging simulation and using exactly the same measures. Yeah.
Is there only a single phantom simulated in the program? Because I saw downloading multiple phantoms actually.
Yes. So you can. So it is. I think there are 20 or 30 different brain phantoms around at BrainWeb, and it's downloading those. And then you can select which one you want to use. In the future, I will also provide other phantoms, which, for example, have some just dedicated, like in phantom on the scanner, which just is a spheric bowl with some holes in it with different T1, T2 values, and also a phantom which supports flow. That's not in there yet, but that will come so that you can also look at flow effects with it. In principle, you can select different phantoms, whatever you like. And right now we just have this one. That one will be resampled based on the information you are giving down here. And just for the for visualization, I want to go to the maximum number of available spins, which is 200 by 200, which takes a while to simulate. But yeah, we simulate it once. So it takes a few seconds. And now it actually already see it has the shape of this magnetization, and it has the T2 values, T1 values of it, but also those field inhomogeneities are also added. So now we can look at what's happening due to those different magnetic fields. Just let's make sure in the settings here that we are showing the color mode phase X, Y, so that the phase, that we can look at the phase. You remember different fields affect the phase of our magnetization. That's what we want to look at. And then you can just click on the play button here. And then you will see, so there are two things happening. So one, in the beginning, our magnetization actually is excited. So it's flipped from longitudinal to the transverse, getting the screen color. And then we already see that there is something going on exactly in this region up here. And that's actually that there is higher precession of the spins. And then we also have T2 relaxation going on. So we are getting contrast in our magnetization as well. And you see that this effect of the different phases, the longer you wait, it just adds on to the additional phase. Yeah, and it even affects at some point regions which are quite far away. But in normal imaging, you won't realize it because the changes are so small in phase that it won't affect your imaging. So the most affected part will be that region. And then going through the imaging, we're just flipping, switching different gradients, so getting different wave patterns. That happens quite quickly. But what we could really actually look into is this region up here. So there you can see, if you zoom in, that our magnetization, yeah, now we are applying the phase, but you can already see that the phase is changing more rapidly in those regions. And that means that we are experiencing signal loss in those regions more quickly. That's a problem. Because in those regions, we do have a dephasing of our signal, which ruins our signal. So the signal we want to measure, if we wouldn't have those field inhomogeneities, this decay would be much slower. Yeah, and we would get a much nicer image, because we wouldn't have this decay. And let me now. And that was actually the main problem when MR started in the 1940s, that they weren't able to create very robust homogeneous magnets. So they were changing, or they had very inhomogeneous fields. So when they were trying to do magnetic resonance, they could excite their signal, but it was decaying very rapidly. So they didn't have a lot of time to actually play around with it and manipulate it and understand what's going on. And that was a huge problem. So that's just what we actually looked at. So we are flipping our magnetization down and then looking at the signal, what's happening. That's called a free induction decay. So we are not doing anything. Are you already asking me to stop? 2 minutes. just having the spin echo explained. Our magnetization will just decay, and if we do have different magnetic fields in close regions, so if we have an inhomogeneous field, then the magnetization will just dephase very rapidly, and our signal decays so quickly. In the laboratory frame, it will look like this. So the mean of our magnetization will precess, but all the individual spins, they will just have different recessions frequencies in the rotating frame. Everything will so the mean will still stay at the same position, so not having any additional phase, but the individual magnetization at different locations, they will experience the different fields, different recession frequencies. And that's actually a term which is compensated, so mathematically described by an additional parameter, which is called T2 prime, which is exactly this effect from those field inhomogeneities. And the resulting relaxation time, as I said, is shorter than T2, and it's called T2 star. So if we are just exciting our signal and reading it out with a certain echo time, we are not getting a T2 weighted image, what we wanted to have, but in so-called T2 star weighted image, which reflects field inhomogeneities that can be used or made use of for functional imaging, but for pure imaging, it often leads to distorted images and poor image quality. And as I said, in the future or in the past, that was a real problem to actually get this to work. And Erwin Hahn experimented with MR in Berkeley back in the 40s of the last century. And what he experienced, he was, because he lost signal so quickly, he just repeated exciting his probe. And here's just an oscilloscope image, what he experienced. So he applied the RF pulse, so that's a really high intensity. So the oscilloscope will just cap this signal because it's so high. And then he sees this very rapid decay. And then he applied the next excitation pulse. He also saw this very rapid decay. But then he saw some signal reforming again. And back then, that was a little bit magic to him. He didn't know where that was coming from in the first. But then he realized what's going on. And he came up with this quite nice cartoon with a racetrack where he says, okay, consider this experiment like a race from two different runners, which are really unfair, which is really an unfair comparison. Because one is really quick, the other one is really slow. But you let them start, and then at a given time, you would just give another command and tell, now return. So of course, the quick runner would be really fast and maybe halfway round. The other one maybe just 1 meter away. But when they are returning, they are just turning around and then running back. They will come back to the start at exactly the same time, because one is really fast but has to run a longer way, and the other one is slow and will but has to go only in shorter distance. And that's exactly the same what's happening with the magnetization by applying several pulses. Because what's happening, and Klaus doesn't allow us to actually play with a teaching tool and show you, but we will do this later. What actually happens is that you flip your magnetization down and then some of the magnetization experience in higher field and others in lower field. So they will just lag behind or be ahead of our reference magnetization. Yeah, that's what I thought, but it's not exactly so. It's in 2 dimensions. So it would be more like this, and then the rephasing is not. I should use this. How it's called, the fans. I wanted to get one of those, but I wasn't able. So sorry. They will just fan out. And what you then do with your second pulse, if you put it correctly, you will just rotate everything around. So that's the command, now come back. You're just applying this pulse along this direction, and that will just rotate the whole magnetization. So all the spins which were in front before are now lagging behind and have to recover, and those which had been lagging before are now in head, and they have a little bit more time, and then they will just come, and then they will just reunite after the same distance between the excitation and the refocusing, and give your what's called a spin echo, because the spins are getting realigned again, and you recover everything which was constant between your start and your spin echo time. So those field inhomogeneities, which are constant over time, you will just be able to recover. But those which are playing on a much smaller time scale, like the neighborings hitting the other atoms and changing the phase, which I explained for the T2 relaxation, those can't be recovered because those are stochastic effects. And that's why we are still getting T2 relaxation, but only T2 relaxation. So we just got rid of this T2 prime component coming from the inhomogeneities. So we removed it from our signal intensity. And that's what this spin echo actually is about. And on a sequence level, it just means that we are using a 90-degree pulse, and then after a while, a 180-degree pulse, and then we are experiencing this spin echo. And we will be able to simulate this with the tool here later on. So thank you so far. And now we are ready for lunch if Klaus doesn't want to say a few more words.
Because these are instructions. Thank you, Matthias.